Welcome to the Explainer. Okay, let's dive right into this, because today we're going to peel back the layers of honestly one of the most fascinating technological breakthroughs of our time, AI image generation. I mean, we're seeing these incredible AI-generated images absolutely everywhere now, right? But what's actually happening under the hood? Like, how does math literally create art? Well, that is exactly what we're going to uncover today. Because this right here, this is the central mystery we're going to solve. How on earth does an artificial intelligence take a simple sentence, just a few words typed out by a human, and transform it into this stunning, highly detailed visual masterpiece? It feels like magic, I know, but it's actually just a beautifully structured sequence of processes. We're going to break down this whole transition from text to visual, step by step, using the actual blueprints of the technology itself.
Now, to understand where we are, we first kind of have to understand where we started. So take a look at this visual representing the reverse stochastic process. In standard diffusion, the AI basically starts with a screen full of pure random static. Think of an old television tuned to a dead channel. Then, through a reverse diffusion process, it gradually, painstakingly removes that noise to reveal an image. But here's the catch. Doing this in what we call pixel space means the AI is agonizing over every single tiny pixel on a high-resolution canvas. It is incredibly computationally heavy, like massively slow.
So to understand how we solve that crazy speed limit, here's our roadmap for the Explainer today. First, a quick recap of diffusion. Second, the latent space shortcut. Third, conditioned generation. Fourth, CLIP, connecting words and pictures. And finally, number 5, the massive leap to video generation.
All right, part 1, diffusion, a quick recap.
Which brings us to part 2, the latent space shortcut.
So to wrap up our thoughts on standard diffusion really quickly, calculating every single imperceptible pixel is just a massive computational bottleneck. If you want a crisp, high-definition image, processing billions of tiny dots one by one it's just not feasible for rapid everyday use. We needed a smarter way for the AI to kind of think about images. And this is exactly where the technology took a massive leap forward. Look at this comparison here. Over on the left, we've got pixel space, which carries all those high-frequency, totally imperceptible details. But on the right, we have latent space. This is an efficient, low-dimensional space that focuses only on the important, semantic bits of the data. Think of it like a sketchbook. If I ask you to draw a beach, you're not going to memorize the exact coordinate of every single grain of sand, right? No, you remember the concept of the sand, the water, the sky. Well, the AI does the exact same thing here. By abstracting away all those tiny details, it works in a lower dimensional, computationally much more efficient space. It's brilliant.
Now, what's really interesting about this slide is how clearly it shows the shortcut. Let's walk through it from left to right. You see the red pixel space over there on the left? The data gets pushed through an encoder, that's the little E you see, and it gets compressed down into that large green box, which is our latent space. And here is the real game changer. It's entirely within this efficient green latent space that the actual diffusion process happens. All the heavy lifting is done in this compressed format. Then, and only at the very end, is it decoded back out into the final stunning pixel image that you actually see.
Let's zoom in just a bit more on that denoising unit sitting right inside the green latent space. Do you see those little yellow blocks labeled Q, K, and V? Those are the cross-attention components. It's essentially a filing system. The Q stands for queries, which is basically the AI asking, hey, what features do I actually need here? And the K and V are the keys and values from your text prompt. Those hold the answers. So this attention mechanism actively matches them up, literally piecing together concepts as the noise clears out.
Moving on to part 3, guiding AI through conditioned generation. So now that the AI can efficiently generate things, how do we tell it what to make?
Exactly. How do we steer the ship here? Well, because the latent space abstracts out the specific, rigid form of the data, it becomes incredibly flexible. The absolutely crucial point here is that we can condition the generation using all sorts of different inputs. We can use text, we can use semantic maps, or hey, we can even use other images. Essentially, almost any data can be converted to feed directly into the latent space. And that attention mechanism we just looked at, it takes these conditioned features, reshapes them, and seamlessly integrates them into the UNet. That's what ensures the final output image is strictly guided by whatever text or image you fed it in the first place.
Okay, part 4, CLIP, words, and pictures. This is the crucial translation engine that connects human language to AI visuals.
Because think about it. If we're mostly using text to tell the AI what to draw, how does it actually know what our words mean? Enter CLIP. To make this magical connection, CLIP uses something called a contrastive loss function, like InfoNC.
Now, I know that sounds super technical, maybe a bit intimidating, but let's just break it down into plain logic. The AI is basically just playing a massive matching game. And this loss function? It's simply the scoring system. It optimizes the alignment of the data embeddings by establishing a really strict set of rules for what is correct and what is totally incorrect.
And this brilliantly illustrates exactly how that matching game works. The AI looks at positive pairs. So, for example, an image of a cat paired with the text, a cat. The contrastive loss function rewards the model for this, encouraging the mathematical distance between these two concepts to be very, very close. But on the flip side, it looks at negative pairs, like an image of a cat paired with the text, a dog. The function strongly penalizes this, forcing those mathematical representations to be super distant from one another. Do this over millions and millions of pairs, and the AI learns perfectly what visual features correspond to which human words. It's honestly beautiful.
Finally, part 5, the future, which is video generation. Because all these foundational concepts we just talked about, they are scaling up massively.
We've gone from agonizing over noisy pixels to zipping through efficient latent spaces. We've used UNets to denoise, and we've used CLIP to perfectly match our text prompts to visuals. But, technology never just stops moving. Just look at the sheer detail of this video prompt from the source material. The camera follows behind a white vintage SUV with a black roof rack as it speeds up a steep dirt road surrounded by pine trees on a steep mountain slope. And it just keeps going. I want to let this massive, highly detailed prompt just sit on the screen for a second. Really think about the unbelievable scale of computation taking place here. The AI isn't just applying CLIP and latent diffusion to a single static frame anymore. No, it's applying these rules frame after frame after frame. It's maintaining temporal consistency, physics, lighting, realistic camera movement, the whole shebang, and it's all dictated by this one single paragraph.
It's just a staggering leap in capability, and it was born entirely out of the foundational efficiencies of latent spaces and attention mechanisms that we just explored together. Which really leaves us with this final thought. We now know exactly how the AI translates our words into these breathtaking realities. So, if an AI can dream up an entire, consistent, moving world from just a single paragraph, what are you going to ask it to build next? Thank you so much for joining me on this explainer today. Keep learning, keep exploring, and I will see you next time.